Hello, my name is Eberhard Kuhn. I am the Marketing Manager for Food and Consumer Products at Shimadzu Scientific Instruments. I will be talking about food contact materials. Are they GRAS or are they GROS? The acronym GRAS, G-R-A-S, is often used in the food industry to indicate foods that are generally recognized as safe. G-R-A-S, GRAS, generally recognized as safe. Here's the outline to my talk. I will be describing the types of food packagings that are available as well as their purpose and function. Then I'll be giving you some definition of food contact articles, food contact materials, food contact substances, and so on, and briefly touch on the regulations. Then we will dive into the contaminants such as mineral oils, metals, organic, and PFAS. And finally sum it up and say, what does this all mean in terms of the food safety? On this slide, we see some examples of food contact materials or food packaging. Now, we all buy food, we all eat food, we all store food, so we are quite familiar with these. The food comes in glass jars, it could come in metal cans, in plastic or cardboard or paper kind of products, typically associated with the fast food industry, for instance. Then we have aluminum pans and things like that, metals, and of course the food storage, the plastic containers that we all use for our own food storage. Food packaging serves a number of purposes. First, it must protect the food. That means it must keep out moisture, it must keep away light, it must keep away pests and bugs, and at the same time it must keep in the flavor, it must keep in the nutrition and prevent spoilage. It must be sturdy enough to allow transportation of the food without damaging it, but it also must provide a surface where there can be information displayed, such as the nutritional information that we all look at, but also give a little bit of opportunity for the manufacturer to advertise their product and give us additional information. But what else comes in contact with our food? There's a long road, what is called the farm to fork, for instance. And so the food starts out on a farm as, say, a chicken or a pig or so, and then eventually ends up on your breakfast table as bacon and eggs. But along the way, it goes to a factory where it's being processed, it's being transported by trucks or trains. There is some containers that it's being stored in. There is the cookware that it's prepared in, and then finally the dishes that it's served on. So there's a lot of different things that come in contact with our food before we eat it. Now let's take a look at some definitions. There are government agencies like the European Food Safety Authority, EFSA, or the US Food and Drug Administration, FDA, that define certain food contact articles and materials. A food contact material is a material that is intended to come in contact with food, and the key word here being intended. So from the beginning, it is designed to come in contact with food, which means it is subject to certain regulations. Those food contact materials include packaging, containers, kitchen equipment, and so forth. The challenge is that they are made from a variety of different materials, such as plastics, rubber, paper, glass, wood, metal, and so forth. Thing that's used in the processing equipment also includes things like coffee makers, where you have the glass carafe and the plastic filter holder and so forth, and sometimes even includes the ink that's used for labeling. There are also food contact substances, and those are substances that are used as components of the food contact materials. But instead of looking at these definitions, let me give you some examples of what these compounds are. Now let's look at a specific example. Starting on the left, we have a jar of Nutella. So that jar is called a food contact article because it is the complete article as you would buy it in the store. Now that food contact article is made up of a number of different food contact materials. In the case of the Nutella, it is a glass jar that has a thin metal foil on top to preserve the freshness. And although it's not shown in the picture, there is actually a plastic lid that goes on top of that. So this food contact article is made up of 3 different food contact materials: glass, metal, and plastic. The food contact materials in terms are made up of food contact substances, such as monomers, polymers, solvents, additives, and so forth. And specific examples of those would be the PFAS, mineral oil, phthalates, bisphenols, and so forth, but also the metals such as lead, chromium. One final term or acronym that you might hear, which is the non-intentionally added substances, NIAS. Of course, there are also intentionally added substances, but the focus is on the non-intentionally added substances because those are the ones we are looking for and the ones we don't know. They're the unknowns, and they can migrate into the food from the food contact materials. And they could be things like unreacted monomers, they could be degradation products, and things of that nature. I want to go too deep into the regulations other than show you that there are regulations in place and you can look them up if you're interested in the details. Often those are 100 pages long, so they would take quite a while to discuss here. So I just wanted to show you that there are regulations in place both in Europe and in the US. This is often the case. Europe is leading the way in these kind of activities. Starting in 2013, the EU Commission already announced its activities there. And as of this year, countries like Denmark are already banning PFAS in paper and board material. In the US, there's also some activities in this area. One of our presidential hopefuls recently introduced a bill to ban PFAS in food packaging. And the state of Washington has identified certain food contact materials as priority products that include cans and the bisphenol that's in the can, and as well as the printing ink. The military is starting to restrict PFAS in military food packaging, and in fact the FDA has recently released a PFAS method for analyzing PFAS in food and will finalize the method very soon. About regulations, let's look at some real science. Let's look at the mineral oil hydrocarbons in food packaging. There are two fractions, the MOSH and the MOAH fraction, the mineral oil saturated hydrocarbons and the mineral oil aromatic hydrocarbons. It's the latter one that includes some potentially mutagenic and carcinogenic constituents. The one we want to focus on, and they do make up to a third of the entire mineral oil fraction. Analytical challenge is that there are many different compounds within the MOSH and MOAH fragments, as you will recall from your organic chemistry. If you take 5, 6, 8 carbon atoms, you can combine them in any number of different structures and isomers. So both the MOSH and MOAH fractions literally have hundreds and thousands of different compounds. See here the levels of MOSH, MOAH and mineral oils in foods can be quite high, and even in food contact materials such as paper and cardboard we see a very significant amount of mineral oils residue. Where are these mineral oils coming from? Well, there are multiple sources. They can come from the packaging material that includes the recycled paper and some of the ink that's used on labeling the foods. But also, anytime there is a machine involved in processing the food, like the one shown here in the picture, or a harvesting machine, so anything that requires a grease or lubricant to function. Food additives such as separating agent, coating agents, and things of that nature. And also, let's not forget that the environment contributes to the food contamination as well. So exhaust fumes from cars can also be a source of mineral oils. In chromatograms, we see the contribution of the food packaging to the food, where we have a jute bag that has been processed, and then there's what's called a batching oil that is used in the manufacture of the bag, and that batching oil is then transferred onto the rice, and so then it ends up in our food. The Shimadzu automated LCGC online system. It consists of a normal phase HPLC that is connected via an interface to a dual column GC system and allows for some additional sample preparation through some additional instrumentation. On the PLC, we first separate the MOSH and the MOAH fraction, so the saturated hydrocarbons from the aromatic hydrocarbons, which then get transferred onto the GC, where we further get separation into the individual components. Now let's switch gears and look at some heavy metals in food packaging. For this experiment, we went to our local supermarket and we bought 3 types of food containers: polystyrene, polypropylene, and polyethylene. We then used what's called food simulants to leach the whatever is in these food contact materials into the food simulant, and then we analyzed for 14 heavy metals simultaneously with a high sensitivity Shimadzu ICP-MS 2030. Summary of the data for the 3 different types of food containers: the polystyrene, the polypropylene, and polyethylene. On the right column, we see the method detection limit, and we see that the method is indeed very sensitive, often in the sub-parts per trillion level. We see that some of the more toxic elements, such as cadmium or lead, we see very, very small amounts, and others like aluminum that are much higher level. This shows a comparison of the 3 types of food simulants that we used, and you can see here that in the acidic food simulants we get a higher amount of metal extraction than just the ionized water. Solutions are, the good news is that all the detected amounts were below the limits defined by the European Union. That there were some differences depending on the types of plastic and also on the type of food simulants we used. While we didn't show the data, it should not be a surprise that there is a correlation to the contact time, with longer contact time leading to higher amounts of material. In our next experiment, we were looking at extractable organics from food packaging. Again, we went to the local market and we bought 3 types of food packaging: a plastic bag, a plastic cup, and some aluminum foil. The samples again were extracted with water and some other food simulants, but in this case they were analyzed on a Shimadzu LCMS 9030 QTOF, scanning from 100 to 2000 m's over Z. Using some special features of the lab solution software, we were able to identify a number of different contaminants in the different food contact materials using the different food simulants. Using Shimadzu Insight Explorer and Lab Solutions browser, we were able to screen these ions and identify 19 unknown ions from both positive and negative modes. We were able to further confirm these ions by looking at the fragmentation data and comparing them to a commercial library, such as the Medlin library for MS-MS. Similar fragmentation patterns between the unknowns and the database basically confirm the identification of those compounds. There are a number of other contaminants in food packaging, such as the UV stabilizers, for instance, benzophenone. Residual solvents can always be present, chlorates, perchlorates, often from the cleaning, the sanitizing, and of course PFAS, and we'll see a little bit more about PFAS in just a minute. People have actually done migration modeling, such as if you look at the bottom, there's a link to the food packaging forum that has done some of this migration modeling. And for that modeling, they have looked at things like the time of contact, the temperature of contact. So for instance, if you take a look at that picture of the hot coffee, that hot coffee will extract more of the food contact materials than, say, an iced tea. Other things like the type of food contact materials, and the surface to volume ratio were also studied as part of this migration modeling. There is a label that you can look for. This is this glass and fork that is a symbol for safe food. PFAS has received a lot of attention in recent years, and it's often called the forever chemical because it doesn't degrade or anything. It stays around forever. But I also call it the wherever chemical, because wherever you look, you will find PFAS, anywhere from drinking water to food containers to cooking ware, for instance, or this bag of popcorn that's on the inside. Because the PFAS, of course, the material itself is great because it's both water repellent and grease resistant. So it does both water and grease at the same time. So good material, which is why it's being used so heavily in the food industry. So what are PFAS? PFAS are a family of compounds that are per- and polyfluoroalkyl substances. And in the past, sometimes they've been called PFCs, perfluorinated chemicals, and there's a whole variety of these materials. And only the PFOA and the PFOS, or the perfluorooctanoic acid, or the perfluorooctane sulfanoic acid, but there's a whole variety. These are the most common ones that have been studied, but there are in fact hundreds and thousands of different kinds of PFAS, short chain and long chain, which makes the analysis quite challenging. PFAS has been a big concern in the environment for some time. And like anything that's in the environment, it will eventually end up in food. So that's why we need to be concerned about PFAS in food. So my colleague who's the environmental manager, and I put together this graph to kind of show the connection of between the environment and food when it comes to PFAS. And you can see from the PFAS manufacturing, it goes into textiles, cookware, and food packaging, from where it goes directly into the food. But in uses for PFAS, of course, is in the firefighting foams, and they are then disposed into the environment, going to the surface water. And while they're being treated, there could always be some residual PFAS in the surface water, especially if that is near a farm, where it could end up on the farm, both in the animals and the agriculture. So you can see this graph is intentionally complicated because the correlation is complicated, but the dangerous part is that we, the people, are sort of the dead end of the PFAS chain, because we accumulate it in our bodies and there's really no natural way of breaking them down. So the PFAS in food is starting to be a very big concern. When it comes to the analysis of PFAS, Shimadzu offers some very good platforms. All our triple quad platforms are very suitable. If the method requires some solid phase extraction, then our LCMS 8045 and 8050 are ideal instruments to use. If there's for direct injection, then the LCMS 8050 and LCMS 8060 are the recommended triple quad platforms. Recently, we did a study on looking at PFAS in bottled water by direct injection, and we had different types of materials. We had a glass bottle. We had, of course, different types of plastic bottles, including the recycled plastic. We had some metal cans and a cardboard, like a milk carton kind of container for water. You can see here in the table that the good news is that in most of the samples we looked at, we didn't see or quantitate any kind of PFAS. Our method detection limit was around 5 parts per trillion, and we only saw two of the PFAS, the PFBA and the 6,2-FTS, in a few of the samples. So where does that leave us? Is there such a thing as a GRAS food container? I recently hosted a networking session on food contact materials, and the consensus opinion by some of these industry experts that were present there was that glass was in fact the most GRAS food container. It can be cleaned more readily, but also just inherently glass is one of the purest substances when it comes to being a food container. The other question is, are today's safe solutions, will they still be considered safe tomorrow? Well, we only know today what we know today. So in terms of the impact that a safe solution today will have, we don't know. There's an incubation period, if you will, of years or decades sometimes before we see any negative health effect on any kind of safe solution that we have today. And an example is, recycling. We all recycle, and recycling is a very good thing. However, it presents some challenges when it comes to food contact materials, because the food contact material that are on the outside, for instance, the ink or so, that's a contaminant. In the recycling process, it can now become part of the actual material and then migrate into the food. So we are introducing contaminants through the recycling process. Now, the recycling industry, and I have to admit I don't know anything about the recycling processes in detail, they assure me that they have processes in place to remove these contaminants so that they don't end up in the recycled products and then migrate into the food. I want to leave you with a more positive image of food. We talked a lot about the food contamination and everything, and yes, there is contamination. That shouldn't prevent you from still enjoying a glass of wine or having some bread and cheese and still enjoying your food. I want to thank you for listening to the webinar today. I hope you found some of the information interesting and useful. If you have any additional questions, don't hesitate to email me at erkuhn@shimadzu.com. I'll be happy to answer your question or start any kind of dialogue or communication with you. Have a nice day.
Excellence in science. Shimazu.